So we learned in a previous video, we learned some things that we know about parallelograms beyond just the definition that a parallelogram is a quadrilateral. Parallelogram is a quadrilateral with both pairs of opposite sides parallel. That's why we call them parallelograms, right? So that's the definition of a parallelogram. So if I were to show you a quadrilateral, right? Then, and both pairs of opposite sides were marked parallel. If I could show you that this was true about some quadrilateral, you would be able to tell me that that is a parallelogram by the definition of a parallelogram. But are there other ways to decide whether or not a shape is a parallelogram? And in fact, there are. We take a lot of the theorems that we learned about previously about once we know that a shape is a parallelogram, we know these other certain things that have to be true. We take those and we kind of flip them around. We take the converse of each one of those theorems basically, and we could use those then to prove that certain shapes would have to be parallelograms. So to give an example, let's look at theorem 5-4 here. If both pairs of opposite sides of a quadrilateral, if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral must be a parallelogram. So in other words, if I can look here and I can say if AB is congruent to DC, so if I could mark these two congruent, and AD is congruent to BC, so I can mark these two. If I could do that, I can say that ABCD must be a parallelogram. This is my little abbreviation for parallelogram, a little parallel symbol, -gram. So if this is true, I can say that without a doubt this shape has to be a parallelogram, even though I don't have any sides that I've marked parallel. If I can just mark both pairs of opposite sides congruent to each other, then it guarantees that this shape is a parallelogram. Well, what else could we do? How else could we decide whether or not a shape is a parallelogram? What if we just looked at one pair, right? If one pair of opposite sides of a quadrilateral are both parallel and congruent. So in other words, if FG was parallel to JH, right? So I'll mark it parallel, and FG was congruent to JH, so I'll also mark that pair of sides congruent, then FGHJ must be a parallelogram. That's what theorem 5-5 tells us, that if these pair of sides are both parallel and congruent to each other, then this shape must be a parallelogram. In theorem 5-6 it says if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral must be a parallelogram. So if I look at this picture down here, and if I were to say that angle K were congruent to angle M, and angle L were congruent to angle N. So if I marked this angle congruent to that, and if I could say that this angle was definitely congruent to that, then KLMN must be a parallelogram. So and again, with both of these, this one I guess I know that one pair of opposite sides are parallel, but I don't know that both of them are. But I know that one pair of opposite sides are parallel and that same pair is congruent. It's got to be the same pair, right? And down here, I know that both pairs of opposite angles are congruent. Again, don't know anything about the sides in this example. I just know that both pairs of opposite angles are congruent. That would give me enough to say that that shape must be a parallelogram. One last theorem that we could use to prove that a certain shape has to be a parallelogram. If the diagonals of a quadrilateral bisect each other, then the quadrilateral must be a parallelogram. So let's put the diagonals in. Let's add in the diagonals. Let's connect our non-consecutive vertices. And I'll go ahead and label that point where they intersect. I'll label that as point M. So this means that in this example, if PM is congruent to MR, and so this is congruent to this, and QM is congruent to MS, so this is congruent to this, then quadrilateral PQRS must be a parallelogram. Now, I didn't go through each of these theorems. I didn't show you the proof, but you can maybe see what it would be. If I kind of back up a little bit, and if I look at this theorem 5-4, well, if I were to add in an auxiliary line here, let's go ahead and do that. Let's add in this diagonal AC. Then what I would be able to see is that, oops, sorry, if I add in this line right here, AC, I would be able to see that these two triangles are definitely congruent, right? Because they're congruent by side, side, side. And if those triangles are congruent, then this angle, let me get my pencil, sorry, this angle would be congruent to this angle by CP/CTC, which makes these lines parallel. Because if it would make these two, AB parallel to DC, because these alternate interior angles are congruent, which means that these two segments AB and DC have to be parallel, right? They would have to be parallel to each other. And then you could say the same thing about this angle being congruent to this angle by CP/CTC, which would make this line parallel to this line, AD parallel to BC, because the alternate interior angles are congruent. And now we have two pairs of opposite sides that are parallel, so by definition this would have to be a parallelogram. So that's kind of what the proof of this theorem would look like. If I were just telling you that these pairs of opposite sides are congruent, you could kind of go through those steps and show that, well, these triangles are congruent, and that means these angles are congruent by CP/CTC, which means these opposite pairs of sides are parallel because the alternate interior angles are congruent, and that guarantees that I have a parallelogram. And a similar proof could be done for each of these other theorems as well. So now let's take a look at some example problems where we're deciding whether or not given information is enough to say that the shape must be a parallelogram. Okay, so for example A, it tells us that from B to E is the same as from E to D, so I can mark those two segments congruent, and C to E is the same as E to A. So with that information, does this have to be a parallelogram? Well, yes, it does, right? Yes, because the diagonals have bisected each other. So if you're a theorem memorizer, this looks like it would be theorem 5-7, right? That the diagonals bisect each other, then we have a parallelogram. So that would be what this case would be. Yes, this is a parallelogram with this given information because the diagonals bisected each other. Example B, let me get rid of my markings here. In example B, we are looking at angle BAD. BAD is congruent to angle DCB. And with that, is it enough information to say that this is a parallelogram? And you might think, oh yeah, look, we got opposite angles that are congruent, so it's a parallelogram. But if you remember, it wasn't just one pair of opposite angles, it was both pairs, right? Both pairs have to be congruent to each other. So in fact, in this case, what we have to say, what we have to say in this case is that no, we don't have enough information. We don't have enough info to say that this is a parallelogram because we only have one pair of opposite angles that are congruent, not both of them. Get rid of that so we can move on to the next problem. In the next problem, we got angle BEA, congruent to angle CED, and angle BEC, congruent to angle AED. Is that enough information to say that this is a parallelogram? Well, no, not at all, right? We knew that those would be congruent. Those pairs of angles would be congruent no matter what, because those are two pairs of vertical angles. So that tells us nothing about whether or not this shape is a parallelogram. So we have to say, no, not enough info for that one. All right, let me get rid of my lines. Next up, we got segment BC congruent to segment AD, and segment AB congruent to segment DC. Okay, now we're in business, right? This is one of the theorems we learned about. This is going to be a yes, because what we have in this picture is both pairs of opposite sides are congruent. So this must be a parallelogram. All right. Next up, segment BC is parallel to segment AD, and AB is congruent to segment DC. So we have one pair of sides that are parallel and a different pair of sides that are congruent. And again, some people might say, oh, yep, I remember something about parallel sides and congruent sides makes the shape a parallelogram. But if I go back and look, it says if one pair is both parallel and congruent, one pair of opposite sides both parallel and congruent, that's when we have a parallelogram. In this case, that's not what we have, right? We have one pair parallel and a different pair congruent. So we have to say on this one, no, not enough info. It doesn't match with what the theorem says makes a shape a parallelogram. So lastly, we have angle BAD, congruent to angle DCB, which is right there, and angle ADC, congruent to angle CBA, right there. So just looking at the pink information on my diagram, is that enough to say that this is a parallelogram? And this one is going to be a yes. This is enough information because, let me write that a little bit neater. Yes, because both pairs of opposite angles we know to be congruent. And that is, if we look back at numbers, that would be theorem 5-6, right? Theorem 5-6 would apply in this situation, and that would definitely be a parallelogram.